Hello everyone, and welcome to my presentation for manipulation planning among movable obstacles using physics-based adaptive motion primitives. This is work I did together with my friend Suhail and our advisor Maxim Likhachev. In this work, our goal is to successfully complete complex manipulation planning tasks in cluttered environments. At a high level, a robot can interact with objects in its environment either via prehensile, pick-and-place style actions, or non-prehensile, push or drag style actions. We call this domain Manipulation Among Movable Obstacles, or MAMO for short. The videos on screen show you examples of prehensile manipulation actions and non-prehensile manipulation actions, and it's borrowed from prior work in this area. We argue that non-prehensile manipulation can be a much more economical planning strategy in scenes like this, both from a time and energy point of view. Often we care about grasping and extracting a single object from the scene, and deliberate rearrangement of the scene via a sequence of pick-and-place style actions can be pretty slow. Also, non-prehensile interactions allow us to manipulate large and bulky objects that are not suitable for grasping. At a more technical level, we might be able to get away with a simple internal model like a collision checker for prehensile manipulation planning. We would require information about whether an object is graspable by the robot and whether the robot can pick it up and move it elsewhere. In this work, we assume that this information about the objects and their models and physical properties is available to us a priori. Contrary to this, while planning non-prehensile robot maneuvers, we need to reason about complex multi-body interactions and propagate their effects via physics-based reasoning. We use an external physics-based simulator in the loop during planning in our work. This means that while it might suffice to search for a valid plan in just the robot's configuration space for prehensile manipulation, for non-prehensile manipulation we need to search in the composite space of all possible robot and object configurations. This immediate exponential increase in the dimensionality of the search space necessitates efficient planning algorithms if we hope to find a solution in a reasonable amount of time. Prior work in this area has tackled the MAMO problems in a couple different ways. The selective simulation algorithm from Saleem in 2020 is an iterative heuristic search algorithm that keeps track of objects that are relevant for the success of a particular planning query and only simulates interactions with those objects. Our comparisons against selective simulation show that our version of heuristic search algorithm for the MAMO domain is up to 20 times faster. KPs from Suhail and Kavraki was designed for problems with complex dynamics models or transition function between states. Evaluating actions in a physics-based simulator is one such example of a model. KPs naively simulates all actions sampled inside a randomized planning algorithm, albeit it tries to explore the workspace of the robot intelligently, but it can be very slow in the MAMO domain because it samples a lot of such actions. In our experiments, we get speedups of up to 40 times over KPs in the domains that we look at. There's also been a lot of work in general in the field of non-prehensile manipulation, with or without considering uncertainty. And we list some examples here, but all these make some simplifying assumptions, such as only planar interactions with the task at hand that we don't make in our work. Formally, we solve a path planning problem for a feasible low-cost solution from a start state for a robot arm to an end effector goal pose. However, the planning problems in the MAMO domain come with object-centric interaction constraints. These object-centric interaction constraints encode whether the robot is allowed to touch an object, move it, topple it, grab it, or not. We place no restrictions on what these constraints can be, so long as the planner can determine whether or not they are satisfied during an action execution. The video shows some ways in which constraints might be violated, and these constraints are supposed to encode things like the robot shouldn't topple a cup of coffee, and a fragile glass object should not be interacted with. So it's not allowed to interact with any red object, which we call immovable obstacles. It's also not allowed to push a green movable object into one of these obstacles. And finally, the movable objects cannot be tilted beyond a certain degree or toppled by the robot. The key observation that led to this work is that for the domains we consider in this paper, we observed that most MAMO planning problems can be solved by restricting robot-object interactions to adaptive motion primitives. Adaptive motion primitives, compared to the simple motion primitives in our heuristic search graph, are longer-range actions. They are constraint determinate in a valid goal state, and they can be generated on demand during planning. The video shows that simple motion primitives, small increments or decrements to individual joint angles, do not lead to rich interactions with the scene. Finding a sequence of these that solves a particular planning problem can be computationally intractable. Adaptive motion primitives, on the other hand, lead to much more diverse interactions with objects and achieve the sort of non-prehensile behavior required in cluttered mammal problems. Pictorially, adaptive motion primitives A1 and A2 are straight lines between some robot configuration, x1 or x2, and some valid goal configuration, xg. We restrict computation of these actions to within a delta ball around the goal configuration. Our key idea then is that if we can find a collision-free path from the start configuration to inside a delta ball around the goal, we only need to simulate adaptive motion primitives. The path from the start configuration to the delta ball around the goal can be found by searching only in the robot's configuration space using a simple collision checker without ever simulating an action, which is very expensive in comparison. Let's walk through an example to illustrate how our algorithm works. Consider this scene where we are given a start configuration and a goal post for the end effector, and on the right we depict the robot configuration space with these points. There are green movable objects and red immovable obstacles in the scene that we need to account for during planning. A naive best first search algorithm will proceed along the least cost path from start to goal, find that any action from some state V interacts with a movable object, O2 in this case, and start simulating all such actions. It could then spend hours simulating all future actions without ever composing a successful sequence of them that reaches the goal and without ever finding an alternative path. Since our algorithm restricts simulations to adaptive motion primitives only, we are able to find a collision-free path from start to some state U within the delta ball around the goal quickly. We can then divide search efforts between improving this path and simulating actions that take us to the goal from a state like U. At the end, we might successfully find a path that moves the object O3 via a non-prehensile interaction caused by an adaptive motion primitive. All this is achieved without ever violating object constraints due to the collision-free nature of the path from start to U and the use of the simulator for action evaluation from there on out. On top of the algorithm we just described, there are some key components that give us important performance boosts. We propose the use of a two-stage planning approach. First, we randomly sample adaptive motion primitives in parallel by spawning multiple simulator instances and selecting a promising subset of them. During the actual planning phase, each of the amps are used to initialize an attractor heuristic in the robot's configuration space. These heuristics are used within our multi-heuristic planning algorithm. We also separate action evaluation during the search to a relatively fast collision checking routine and a much slower physics-based simulator. The collision check quickly lets us determine whether we need to simulate an action at all. This is true only when the collision checker determines that an action intersects a movable object and does not intersect any immovable obstacle. If we do simulate an action and determine it violates object constraints, we delay simulating similar actions where similarity is based on distance in the configuration space of the robot. In the paper, we present numbers for planning problems in two domains, a tabletop workspace on the left with 12 objects, 6 movable and 6 immovable, and a smaller, more constrained refrigerator workspace with 3 movable and 2 immovable objects. The quantitative evaluation shows that we are up to 40 times faster than state-of-the-art baselines. For this presentation, we'll limit ourselves to showing you cool real-world videos of our PR to successfully picking up a box of crackers, which was especially delicious late at night when we were running these experiments. We'll show you 3 runs of the tabletop scene, followed by the robot grabbing the same cracker box from within a cabinet and also from within the freezer of a refrigerator. In all these experiments, we're using objects from the YCB dataset, and we're using a perception algorithm developed by a student in the lab, Perch 2.0, that runs on the GPU and gives us relatively accurate pose estimates for the objects. Within the simulator, each of these objects is initialized as being movable with 75% probability, and we're always asking the robot to pick up the cracker box, because I guess we're hungry grad students. Thank you for watching my presentation, and I hope you enjoy the conference.